Yeah, I'll go really fast through these. I'm not going to do all of them, but some of the more popular ones. Like, for example, D, to do the integral of 2 cosine of 4x dx. So we have an inside function of 4x, so that's what we're going to let our u to be. So u equals 4x. So therefore du is 4 dx. And so solving for dx gives us du over 4. So we'll make the substitution. 2 cosine u du over 4. 2 and a 4 cancel, give you 1 half. So that's that. You integrate that, that's sine, so 1 half sine u plus c, so 1 half sine 4x plus c. So that's the answer. And we can check by the derivative all of this stuff. E sine x e to the cosine x dx. It's a product. We cannot integrate products term by term. We need to get more creative. And again, what we notice, we have an inside function of cosine x, and the derivative of that is sine x. So that's our substitution. U is cosine x.
There's actually 3 cosine x.
Oh yeah?
That matters, doesn't it?
That matters not by much. So du is negative 3 sine x dx. So solving for dx gives you du over negative 3 sine x. So when you make the substitution, sine x will cancel. So you get sine x e to the u, and then du over negative 3 sine x. So sine x cancels with sine x, negative 1/3 comes out, e to the u du. Okay? And the integral of e to the u is e to the u, so you get negative 1/3 e to the u plus c. Here we go. Is it supposed to be warm next week? What?
I hope so.
That means they'll go outside. That's what we're talking
There's
about.
no reason to stop.
All right, tangent x. A very common mistake was that the integral of tangent x for some reason is secant squared x. Well, the derivative of tangent x is secant squared x, not the integral. So the way we do that one, we express it as sine x over cosine x, and we realize the derivative of cosine is sine. So it has that natural log case to it. So u is the denominator and du is the numerator. Okay? You can make a substitution without really solving for dx, because you see how you have sine x dx, which is negative of du. So you can make that substitution with a negative du over u, which is natural log of u. And you substitute. Get that. Is that okay? So don't mess up derivatives with antiderivatives. G, that's a straight up substitution. You have a cubic and a quadratic. So we're going to let u equal 1 plus x cubed. So then du is 3x squared dx. Right? Solve for dx. U over 3x squared. x squared cancel with x squared, so we're left with, if I rewrite this, is u to the negative 1/2 power du. And when you integrate that, you add 1 and you divide by 1. And I'm losing a third, right? There's a third. So that really becomes 2/3 square root of u. I'm going to substitute back. So we get that. Is that okay? All right, so h and I are basically the same problem. If you do the substitution properly, cosine root x over root x dx. So when in doubt, try to go for the inner function. U is the square root of x, so then du is 1 over 2 square roots of x dx. So that gives you that square root of x in the denominator. So if we solve for dx, we get 2 square root of x du. So making a substitution, square roots cancel. You still have that 2. I didn't mean to cancel that 2. But 2 comes out, so that's cosine u du. So that's 2 sine u plus a constant, which is 2 sine squared of x. Does that make sense? Yes? So same thing with the next problem. The next problem, we have cosine of pi over x squared, trying to integrate that. So the same story, let u equal the inside function, then du is the derivative of that dx. So that's our x squared in the denominator. Is that okay? So solving for dx gives us negative x squared over pi du. So when you make a substitution, we get cosine of u over x squared times negative x squared over pi du. So x squared cancels with x squared. Negative 1 over pi comes out. Leaves you with that. So same problem as before. We'll integrate that. So it becomes sine of u plus a constant, so negative 1 over pi sine of pi back. Is that okay? So any questions on like the first set of integrals? I didn't do some of the first ones, but you should be okay with like first 3 at least. All right, well, let's keep going. So people making an error with the signs here. That was mostly okay. So the integral of that is x squared minus 3x evaluated from negative 2 to 3. Do that derivative. So you plug in 3, that's 3 squared minus 3 times 3 minus, and that's where you have to watch your signs. First gives you 0, 9 minus 9. So it's negative, that's 4 plus 6, so negative 10. On the next one, the trick there was to realize that we have to divide by x squared. Okay? So if you divide both terms by x squared, you get x squared plus 1 over x squared. And then do the integral. Otherwise, you cannot do that. So integral of x squared is x cubed over 3. Integral of 1 over x squared is negative 1 over x. Value if you want it. Is that okay? So then plug in the numbers, blah, blah, blah. You get something out of it. 0 pi over 2 secant x tangent x dx. So there you have to remember the derivative of secant is secant tangent. Therefore, the antiderivative of secant tangent is just secant. So the integral of secant tangent is simply secant x from 0 to pi over 2. Okay? So for now, we're in trouble in this one, technically. Because when you plug in pi over 2, that is undefined. So it involves division by 0. Right? So say something like that. In Calc 2, we'll play more with problems like this when one of the limits is an asymptote. That's what it is. Secant has an asymptote of pi over 2. So sometimes we can do stuff to it. D from 0 to pi over 4, 1 plus cosine squared x over cosine squared x dx. Well, that's same as question B. Divide everything by cosine squared, so we should get. So if we do that, that's 1 over cosine squared x plus cosine squared x over cosine squared x. So that's secant squared plus 1. Is that right? Two nice functions that we know how to integrate. Integral of secant squared is tangent. So this is tangent x plus x, evaluated from 0 to pi over 4. So tangent of pi over 4 plus pi over 4 minus big 0. Tangent of pi over 4 is 1. Whatever that is. Good. Questions on this one? Because the next one, that's when things start to get a little tricky. So we have 1 plus 2x and then that lonely x. That lonely x kind of throws us off. But still, let's just go with that inner function thing. Okay, because if we can get it in a form like the previous problem where we have a single thing in the denominator, then we can start dividing. One thing in the denominator, many things in the numerator is better than one thing in the numerator and many things in the denominator. Do you realize that? Because when there's just one thing, you can start dividing. Well, that's not the case here. You have one thing in the numerator. So we're going to let u equal that inside function. 1 plus 2x. Then du is 2 dx. Right? So dx is du over 2. But if I make the substitution the way it's written, nothing is going to kill that x. So I can solve for x in this expression. I can solve for x. I can say that x equals u minus 1 over 2. So I'm going to make that substitution as well. Okay. Now it's also a definite integral, so I should also change my limits of integration, u of 0, u of 4. Instead of x, I'm going to put u minus 1 over 2 divided by square root of u, and then du over 2. I have over 2, that's over 4. So 1/4 comes out. U of 0 equals 1. U of 4 equals 9. Right? I can just do that so I don't have to go back to x. And then everything that I have is u minus 1 over square root of u du. Then I can divide each term by the square root of u. And if I do that, I get 1/4 integral from 1 to 9 square root of u minus 1 over the square root of u. Right? U divided by square root of u, square root of u. So this is and that's a simple antiderivative. So that's u to the 3/2 over 3/2 minus u to the 1/2 over 1/2 valued at 4. Now whatever that equals. So this is 1/4. So 2/3 square root of 9 cubed minus 2 square root of 9 minus 2/3, well, times 1 plus 1/2 times 1. So whatever that is. 1/4. This is square root of 9 is 3, cube it 27, divide by 3, back to 9, multiply by 2, 18, minus 6, minus 2/3, plus 1/2, or whatever. Right? It's almost tricky.
I'm just a little bit lost where I can see how it's done, but how did you know that it was time to substitute in to change the limits?
Well,
Because we solve for x over there?
well, if I do this, say it again.
Is it because when we solve for x out of that original u equals 1 plus 2x, that's when we know that then it's time to change the limits?
You mean those limits?
Yeah.
Well, every time you do u substitution, you're going to change those limits. If you have a definite integral and you're putting it in terms of u, the limit is going to change.
Oh, okay.
Now, the reason why I thought you were asking how I need to solve for x.
No, I see that. I missed it in the test, but I see why. But like, for example, okay, I gotcha.
Because when you do definite integrals with u substitution, your variables change, so your limits change.
I see.
So, I mean, you can do the entire antiderivative, put it back in terms of x as a definite integral, and then keep the original limits, but it seems redundant.
Gotcha. Okay. So anytime you're using the u substitution,
Yeah.
it's indefinite.
Right.
Okay.
So this way you don't have to go back in terms of x.
I need the redundancy of that.
What?
I said I need the redundancy of that. So I put it back into x.
Well, that's okay. It's extra step. I think all you got that question for some reason.
E.
What?
E.
What?
E.
No.
Okay.
Oh, okay. Well, I guess not all you got that question. What did you get?
I got that.
No, I mean, what is the answer to that question? Zero. Right? Is that what you were? You didn't get zero?
I did not get that.
Oh, okay. Well, that is zero. Why is that zero? It's an odd function integrated over symmetrical integral, right? Now, I should have smacked Cheryl down for just saying that and not showing me how that's an odd function. Because I don't think anybody did that. You just say, oh, well, it's an odd function, so I want that to be zero. That's just cheap. But we know that that's an odd function. If f of x equals this, then f of negative x equals sine of negative x over 1 plus negative x squared. Now, since sine is an odd function, negative comes out in the numerator while denominator stays the same. So that negative can be pulled all the way up front, so that's negative f of x. So that's the definition of an odd function. F of negative x equals negative f of x. And then we know when you integrate an odd function over an interval that is symmetric around origin, you're always going to get zero. Because one area is the mirror image of another area reflected on the x-axis. Okay, good. All right, so now that you got tricked on question 3, because I'm asking you to differentiate the given functions. I'm asking you to find the derivative, so if f of x is defined to be an integral from negative 2 to x, 2t minus 3 dt, all you have to do is to find f prime of x. There is a long way of doing that by actually integrating it and then differentiating it, but you have a theorem that tells you it's just that. It's whatever the integrand is evaluated at x. You have a theorem that says that. Right? That's what Steve covered that with you. Let's see. Integration. Fundamental theorem of calculus. There are a few of those. So that's, well, anyways, somewhere in there. I'm having issues with my Wikipedia. Where is it? I don't see it now. Well, anyways, we talked about that in class, so yeah, here we go. Is that the one? Yeah. When you integrate, here we go. Derivative from a constant to x of a function is just that function at x. Right? But anyways, even if you do it the long way, it should come out. Now for B, that's a little tricky. If f of x was defined to be from 0 to x cubed sine of t squared dt. Now this one you cannot really integrate that function until you can. But if we follow the same theorem, then the derivative is whatever this function is evaluated at that upper limit. So that's sine of x cubed squared, but then by the chain rule, times the derivative of that function. So that is 3x squared sine of x to the power 6. But I wasn't really taking any points for that. Well, the last question, C. What's the derivative here? This thing right here is defined to be a constant. That's a constant, right? It's from -2 to 7, whatever that is, it's a constant. What's the derivative of a constant? What? Here. Well, if you evaluate that, it's a definite interval from -2 to 7. You can compute it. It will come out to be a constant, right? The integrals show up as constants if you actually evaluate it. What?
I went the long way.
But even if you go the long way, you'll get some kind of an answer, which is a constant. You take the derivative of that, you still get 0. Okay. So the last question. Given the acceleration, and given these 2 points, where s is the position function, I want to find the position function. So find the position. So we know that acceleration is the second derivative of position. So in order for us to get all the way back to position, we need to integrate acceleration twice. Right? Velocity would equal to the integral of acceleration, and position would be the integral of velocity. Right? Because derivative of position is velocity, derivative of velocity acceleration. So first, finding velocity. So velocity is the integral of acceleration, which is 10 sine t plus 3 cosine t dt. So that gives us -10 cosine t plus 3 sine t plus a constant. Right? So if we had any information about velocity, any extra points, we should be able to find that constant. But we don't. We don't have any information about velocity. So let's keep doing integration. So the position will be the integral of velocity. So I'm going to integrate the way this function is written, keeping that constant c. So then we get -10 sine t minus 3 cosine t plus c is a constant, so the antiderivative of c is c times whatever variable we have, which is t, but then plus some other constant. So that constant most likely will be different from c, so let's call it a d, whatever. Now, since we have 2 pieces of information, we know this, and we know that, I can find those constants. Okay? I can solve for c and t. So for example, s of 0, that means -10 times sine of 0 minus 3 times cosine of 0 plus c times 0 plus d equals 0. Right? The reason why it's equals 0 on the right Okay? Now, since sine of 0 equals 0, cosine of 0 equals 1, c times 0 equals 0, we're left with negative 3 plus d equals 0. Right? So what is d then? D equals 3. So that implies that d equals 3. So for now, the position is negative 10 sine t minus 3 cosine t plus 3 times, d is plus c times t plus 3. That's what we have. We found t to be 3 in the previous case.
Oh, because t goes to 0.
Alright, because over here when you plug in 0 for t, so you just... Well, now I can find t, because I know s of 2 pi equals 12, so it's negative 10 times sine of 2 pi minus 3 times cosine of 2 pi plus c times 2 pi plus 3 should equal to 12. Because that's another given. Now, sine of 2 pi equals 0. Cosine of 2 pi equals 1. So we're down to negative 3 plus 2 pi times c plus 3 equals 12. So 3's cancel. We're down to 2 pi c equals 12. So therefore, c equals 12 over 2 pi, or 6 over pi. So the answer then is this function, negative 10 sine t minus 3 cosine t plus 6 over pi t plus 3. What?
So close. I didn't think about doing the thing with D. I tried to treat both C's similarly.
Yeah, that's because again, those constants do not have to be the same. It's just some constant, so they're not necessarily equal. Well, in this case, it didn't, because, well, yeah, in this case, yeah, that c disappears with no hours. Because basically, again, what it gives you two equations with two unknowns. But the first equation is just simple, because one of the variables dies, so we're done. Alright, so that's our test. And I didn't really grade it like usually, each problem is whatever points. I didn't even know what was what. It was more of a, looks like whatever. Well, because I mean, otherwise there's some bad situations. I was going to give you an extra credit assignment to help those bad situations, but those bad situations are not here. So, I don't know. I don't know. We'll see. So was that our third exam? Nice. So we're just on the final stretch. All right, so we started our discussion of inverse trig functions. So, which basically puts us at the end of chapter 5. Yeah, so this is the so we kind of derived that. So we derived those. Not all of them, but we derived arc sine, arc cosine, and arc tangent. We derived the derivatives of those three. Now, we didn't do arc cotangent, but it's just negative of arc tangent. And we didn't bother deriving this last two. And yeah, we just didn't bother. Be aware of this, of the arc secant, arc cosecant. Know where to look them up, if necessary. I'm not going to ask you to memorize those two, but you should be somewhat familiar with definitely the arc tangent. Because we also agreed that just in general, the derivative of arc sine of x is 1 over square root of 1 minus x squared. So if your u is x, so that's what you get. So this is the simple form. The derivative of arc tangent is 1 over 1 plus x squared. And the derivative, so basically if you have an x, so your u prime becomes 1. So for example, again, the derivative of, let's say, arc secant x would be 1 over absolute value of x, and then x squared times 2. So if you u equals x, that's what happens. Is that okay? Now, integrating. Integrating these things. Now, when I'm talking about integrate, I'm talking about integrating the derivatives of arc sines. I'm not talking about integrating the arc sines yet. That's a little messy. Okay? But for now, I just want to show you a few examples when we try to integrate functions that maybe just look like the derivatives of inverse trig. Okay? So I'm just going to start with an example. Very simple example. Integrating dx over the square root of 4 minus x squared. It doesn't have to be 4, it could be any perfect square, really. So look, if you look at this expression, so you have basically 1 in the numerator, yeah, 1 in the numerator, and in the denominator you have a constant minus x squared on the square root. Which one does it kind of look like? Arc sine, right? Arc sine, it's just the difference is instead of 1, it has 4. Okay? So if we go back here to our arc sine, looks like 1 is kind of a big deal, while x could be any other function, right? It could be any function. So if I try to fake 1 instead of that 4, so I have to do some factoring. So I'll pull out a 4. If I do pull out that 4, that leaves us with 1 minus x squared over 4, like that. So see what I'm doing? I'm trying to fake that 1. So I can take the square root of 4. It will come out as a 2. And that's a 2 in the denominator. So I can pull it out. It's just a big 1/2. So that's what happened to that 4. It came out as 1/2 on the outside. Okay? Well, now look. In in my rule, it says u squared, so I should have some function squared. Well, right now, I have x squared over 4. Can I express x squared over 4 as something squared? What squared equals x squared over 4? X over 2, right? I can express that as x over 2 squared. So now it really matches that, that rule. Then I have 1 minus x over 2, right? 1 minus something squared. Now I can really now get a little more sneaky. Because look at the relationship that I seek. I have a function, and then I have a derivative of that function. See that? I have a function squared, and then I have a derivative of that function. Right? Well, if I go back, what is that function? What is u? X over 2. And what's the derivative of x over 2? 1/2. So I kind of have that as well, right? I mean, we're just so used to kicking the constants out, but really, that's my u prime, right? Even if I don't notice it and I start doing the u substitution, I'll say let u equal x over 2, then du equals 1/2 dx, right? Well, here's my 1/2 dx, right? So that's du. So then it becomes a perfect setup. Du over the square root of 1 minus u squared. Which that gives me arc sine of u. So that's arc sine of x over 2 plus a constant. Okay? Now your book kind of gives you a rule that just does it for you without really messing with all those extra steps. But I wanted you to see those extra steps, where all that comes from. Now let's try to do another one. That one might take a while. Did I not start from the first page again? Oh, I did. That one's good. So integrating dx over 2 plus 9x squared. Okay. Now this is going to be really messy to do if we just do it the long way. But anyways, let's try it. We might get a bunch of square roots. And let's just not rationalize it. Get another. We're grown-ups. Now, if you go back to that, I mean, the only options are arctangent or arctangent, right? And really, if your only options are arctangent or arccotangent, it really doesn't matter which one you use. We're just going to use arctangent, right? That's what we agreed on. If it sounds like a horse, yeah, not a zebra, right? That's we use that analogy. Yeah, the zebra syndrome, right? Yes. That's not what, anyways. But we need to do a lot of fakeage here, right? Yeah. I will have to do a little Krishna, let me see it. Oh my God. Anyway, so I should have just given you the nice little rules without making you suffer. We like that one, right? So you gotta get that one in there. So that means we're gonna have to factor the 2 out. Right? So 1/2 is kind of a constant. So 1/2 comes out. Now we also want our second expression to be a perfect square, so I have to write it as 3x over the square root of 2 squared. That's how I have to write that. Okay. So let u equals 3x over the square root of 2, then du is just 3 over square root of 2 dx. Right? So that means dx equals square root of 2 over 3 times du. Is that okay? So when I make my substitutions, I have 1/2. Now dx becomes that, so I can pull that out, square root of 2 over 3. And then that gives me an integral of du over 1 plus u squared. Okay? And I'm going to do something silly. Because again, we're eventually going to look at the rules. And those rules will help us. But you see, without the way it's written, that constant up front, that's square root of 2 over 6. Right, that big constant up front. This is square root of 2 over 6. Right? Which is nice and happy, does not have any radicals in the denominator. But we will see a pattern later, so I'm actually going to go ahead and reduce that. Because 2 is square root of 2 squared, right? If I square that, I get that. So I can actually make a reduction. Square root of 2 cancels with 2, leaves us with a square root of 2 in the denominator. Because 2 is square root of 2 squared. So that's a 1. Because you will see a little pattern in the end. So it's 1 over 3 square roots of 2. The integral of that is tangent u. So when you substitute back, right, it's 1 plus u squared. And u was 3. Oh yes, our thank you. Yeah. Square root of 2x. Now, does that make sense? How we did that? Your book has these rules, the general rules, that the integral of 1 over the square root of a squared minus u squared du. So this is kind of what we had in this first example. Have a constant minus function squared. The general rule here is 1 over a arc sine u over a. actually no. I'll take this back, no 1 over a. Because if we go through the same motions as we did in our example, our a, in this case, if you compare this problem with what I just wrote, with a squared minus u squared, a is 2. Do you know that? And in the end, our answer came out to just arc sine of x over 2, where x is u. And that seems to balance with this rule, right? So arc sine of u over a. Now, general case for the arctangent, 1 over a squared plus u squared du. In this case, we have 1 over a and then arctangent of u over a. Now, if I compare that to my problem we just did with a lot of extra steps, 2 was that constant, right? 2 plays the role of a squared, right? If 2 is a squared, what is a? If 2 is a squared, what is a? Square root of 2. So this says put 1 over square root of 2 up front, and this is kind of what we have. We do have 1 over square root of 2 in our answer. Now, u squared is 9x squared. So that means u is 3x, okay? Based on this analogy, when I'm comparing this line to that line, u squared is 9x squared, so that means u equals 3x, right? So this says 3x over a, so here's our 3x over the square root of 2. The only extra thing that we have in our answer is that 3. And 3 comes out as the derivative of u, because the derivative of u is 3, so you need to kill that. So that's 1/3. The 1/3 will come out if you do the proper u substitution. Okay? So, for example, if you were given this, let's say dx over whatever number, 5 plus 7, I should have kept that. Okay, whatever. And again, I'm trying to compare that with this. I'm trying to compare that with du over a squared plus u squared. So what is a in this case? Square root of 5. And what is u? Square root of 7x. Right? So when I make that substitution, the only thing I need to solve is for dx, right? So du is just square root of 7 dx. So dx equals 1 over square root of 7 du. Okay, so that's what I'm going to be missing. But now I can just go ahead and make my substitution. Okay, because this now is du, so it's 1 over root 7 du over, I keep writing that square root, over square root of 5 squared plus u squared. So the rule tells me it's just 1 over a inverse tangent of u over a. So it is 1 over square root of 5 Now I also have that 1 over square root of 7. That was part of the dx. And then inverse tangent of u over square root of 5. And u is that. So it is 1 over the square root of 35 inverse tangent, and then square root of 7 over 5 x. Also constant. So this is, well, I'm not a big fan of using these formulas. Because if you use these formulas, you forget about the du. It's really easy to lose that. If your u is not a simple function, it's easy to lose that constant. You can do it the long way, just do substitution. Get 1 and then get a perfect square and then do the substitution. I think it'll work better. Fewer things to memorize. Okay, let's try this example. So this is a little more fun. Trying to integrate dx over the square root of e to the 2x minus 1. So because of that, we have a whole new function in there, so in no way it looks like any one of those derivatives here, right? Because of the e to the 2x. But we do like to have some function squared under the radical, right? Or just some function squared, period. Well, e to the 2x, is that a square of some function? What function squared equals e to the 2x?
E to the x.
E to the x, right? So I'm going to let u equal e to the x. Then du is also e to the x dx. So that means dx equals du over e to the x. Right? And what is e to the x again in this problem? U. So dx is du over u. So when I make the substitution, this becomes du over u divided by the square root of u squared minus 1. Right? So this is du over u times the square root of u squared minus 1. So I have that extra u in there. Is that okay? So if I flip back to my little table, what does that look like? Yeah, arcsecant, right? It has absolute value of u, but our u is always positive because it's e to the x, so we need the absolute value. So it does look like the arcsecant. And we don't need to worry about the u prime. So that looks like arcsecant of u. So this is arcsecant of e to the x. Is that okay? We can run into this type of scenarios. just begin an example. I'm going to do an example study. So we already saw that square root. That looks like the square root that gave us the arc sign on one of the early examples we did today. But the numerator is all messy. But I can split that. I can make it into two functions. I can think of this as an integral of x over the square root of 4 minus x squared dx plus 2 times the integral of just 1 dx over the square root of 4 minus x squared. Okay, I can do that. That's algebraically allowed. Now, the second integral, we already did that one. Remember, we turned 4 into 2, factoring it out. That gave us the arc sign of x over 2. While the first integral, that's just a standard U substitution. Because the derivative of the inner function appears in the numerator. So for the first one, if I let u equal 4 minus x squared, then du is negative 2x dx, right? So dx equals du over negative 2x. So if I make the substitution, x over the square root of u, and then du over negative 2x, plus 2 times arc sine of x over 2, because we already did that one. Right, we did that second integral earlier. Okay, I mean, it's right here. Yeah. So x's cancel in the first one. We still have negative 1/2. Integrating u to the negative 1/2 dx plus 2 arc sines of x over 2 plus cos. Yes, du. So then negative 1/2 u to the 1/2 divided by 1/2 plus 2 so 1/2 will cancel. So you're left with negative square root of u plus the arc sine. And then substituting back, what was the u? 4 minus x squared. So that's that. All right, things get really funky if we do something like that. Dx over x squared minus 4x plus 7. So that looks a bit ridiculous. All that is in the denominator. Do you see why that's ridiculous? You can't just... Yeah. If that denominator, if we could factor that denominator, then there are certain Calc 2 techniques that we can use if that denominator is factorable. But this one is not. Okay? This one is not factorable. And there are no square roots in the denominator. So our only hope is to maybe make make it to look like that, where it has a perfect square plus a constant. Right, again, that 1 is a constant. That's really what it is. So perfect square plus a constant. Well, the way you take a quadratic and turn it into a perfect square plus a constant is by using one of your favorite algebraic techniques called completing the square. Remember what I'm talking about? We can totally do that. I can say, well, x squared minus 4x plus, what do I need to add to make that a perfect square? Remember how we take that 4, you divide it by 2, and you square that. So I'm going to have to add 4, right? But I can't just add 4 randomly, I also have to subtract 4. So I have to make sure I don't change my original problem. So in reality, I'm adding 0, which is totally fine. So that means this thing becomes x minus 2 squared plus 3. So that's what that polynomial written as a perfect square and whatever. So I can actually think of this, and let me write it in the form that is more arctangental. Actually, I'm going to use the formula for integration here because my u is x minus 2, right? That's my u. And the derivative of that is 1, so I don't have to worry about that extra.
Sorry. I know continuous square is real, but how did you get plus 0 there?
Well, because I added 4 and subtracted 4 at the same time. So that's really not changing anything. This 4 became part of the perfect square. That negative 4 turned 7 into a 3. Okay? That's all right. So I'm actually going to use the formula that we have derived earlier for the arctangent. My u is x minus 2, and du, I don't need to worry about it, du is 1. And a is square root of 3. Right? Because I had 3 there. So a is square root of 3. So therefore, the integral there is 1 over the square root of 3 arctangent of x minus 2 over the square root of 3 plus a constant. Just using that formula straight up. Okay, the formula that we derived earlier, that du a squared plus u squared is 1 over a arctangent u over a. Because again, in this case, I don't have to worry about du, so because du is 1. So yeah, sometimes you have to complete the square. So that kind of creeped in out of nowhere. How's that? Oh, you were gone last 10 minutes. Of course it's confusing. Yeah, that's okay. It is confusing. All right, good. I'm going to stop at this point.